In chapter 10, that is some applications of differential geometry, in this module, that means module 5, we shall learn about the applications of differential geometry in general theory of relativity. Now, general theory of relativity is slightly different from special theory of relativity, which we have learned in our module 4. Here the gravity or the gravitational force has a great impact on the space time. Now, in this module, that means module 5 of chapter 10, we shall learn a special type of metric for a space time, that is called spherically symmetric space time, and in this module we shall learn about the Schwarzschild metric, and we shall see that the Schwarzschild metric is a static metric. Static metric means it is time reversal. That means in place of t, if we take minus t, then also the line element remains same. So, all these things we shall learn in this module. So, title of module 5 of chapter 10 is Applications of Differential Geometry in General Theory of Relativity and Cosmology. Here we shall mainly learn about spherically symmetric metric, and that is specially a Schwarzschild metric. Now, Einstein developed general theory of relativity in 1915, that is 100 years back, in order to discuss gravitation. In general theory of relativity, the geometrical structure of the space is pseudo-Riemannian. That means, the line element is not positive definite. Here we shall discuss a special type of metric only for this module, known as spherically symmetric metric. The general form of the line element for a spherically symmetric space time with respect to the coordinate system r, theta, phi, t can be written as this one. This is the line element d square equal to p dt square minus 2q dt dr minus u dr square minus v d theta square plus sin square theta d phi square. T is the time factor here, time coordinate, and r, theta, phi are the space coordinate. So, for spherically symmetric space time, at first we can write in this form. The line element can be written in this form, where p, q, u and v are functions of t and r. Now, if we choose r equals to square root of v as a new radial coordinate, because r is the radius of the space. So, we are taking r equals to v to the power of 1 by 2 as a new radial coordinate. The above line element will take the form in this way: d square equal to p dash of the function of t and r dt square plus 2 q dash, it is also function of t and r dt dr minus u dash dr square minus r square in the bracket d theta square plus sin square theta d phi square, and arranging the terms we can write in this form at 1 by p dash dt minus q dash dr whole square minus in the bracket q dash square by p dash plus u dash dr square minus the last term r square d theta square plus sin square theta d phi square. Now, in general, p dash dt minus q dash dr may not be perfect differential, but if we multiply by some integrating factor like WTR, the expression becomes exact, and in that case we can write that exact form in dt equals to W p dash dt minus q dash dr. So, W is the integrating factor here, which makes p dash dt minus q dash dr into an exact form. So, the line element with this new time coordinate becomes, so capital T becomes a new time coordinate, and the line element will take with the new time coordinate in this form 1 by p dash w square d capital T square minus in the first bracket q dash square by p dash plus u dash dr square minus r square d theta square plus sin square theta d phi square. Now, if I write p dash w square to the power minus 1, that means if we substitute 1 by p dash w square by e to the power nu and q dash square by p dash plus u dash as e to the power lambda, so that the line element takes the simple form d square equals to e to the power nu d capital T square minus e to the power lambda dr square minus r square within the bracket first bracket d theta square plus sin square theta d phi square. So, this is the general form of the line element for a spherically symmetric space time, where the two unknown functions nu and lambda are functions of capital T and R. Now, this one can be also expressed in this form d square equals to minus e to the power lambda dr square minus r square d theta square minus r square sin square theta d phi square plus c square e to the power mu dt square, where c is the velocity of light. Now, we shall determine the values of this mu and lambda in our next steps. Where lambda, mu are functions of R. Now, the coefficients of dr square and dt square have been selected as exponentials in order to ensure that the signature of d square is -2. And we have also seen from our previous slides that d square have the exponential terms. Now, let us replace x1 equal to r, x2 equal to theta, x3 equal to phi, and x to the power 4 equal to Ct. Then the non-zero components of the fundamental metric tensor are G11 equals to minus e to the power lambda, G22 equals to minus r square, G33 equals to minus r square sin square theta, and G44 equals to e to the power mu. So, these are the coefficients of the fundamental metric tensors Gij, which we have learnt in our previous chapters. And other Gij's are 0 for I not equal to j. Then the determinant of Gij, generally we write it in as G, is equal to minus r to the power 4 e to the power lambda plus mu sin square theta. So, the determinant of Gij is coming to this expression, and thus we can find the non-zero components of the conjugate symmetric fundamental tensors, that is the contravariant reciprocal tensors G upper 1 equals to e to the power minus lambda with a minus sign, G22 equals to minus 1 by r square, G33 equals to minus 1 by r square sin square theta, and G44, that is G upper 44, equals to e to the power minus mu. So, these are the components of conjugate symmetric fundamental tensors, and with the help of these Gij's and upper Gij's, we can find the Christoffel symbols for this metric, and we have calculated all the Christoffel symbols. So, here the Christoffel symbol of first kind, that is 1 1 comma 1, is coming to 1 by 2 del G11 by del r, and if we just take the partial derivative of G11 with respect to r, then it is coming to minus 1 by 2 e to the power lambda lambda dash. Where this dash denotes the differentiation of lambda with respect to r. So, wherever this dash will be there, it means that it denotes the differentiation with respect to r. And consequently, the Christoffel symbol of second kind, that is gamma 1 1 1, which is equal to G upper 1 1 Christoffel symbol 1 1 comma 1, and it gives half lambda dash. And similarly, we can easily calculate, you can try to calculate these values, that is gamma 1 2 2, all are the components of Christoffel symbols of second kind. Gamma 1 2 2 is coming to minus r e to the power minus lambda, gamma 1 3 3 equals to minus r e to the power minus lambda sin square theta, and gamma 1 4 4 is equal to 1 by 2 e to the power mu minus lambda mu dash, where again mu dash means the differentiation of mu with respect to r. And gamma 2 1 2 is coming as 1 by r, gamma 2 3 3 equals to minus sin theta cos theta, and gamma 3 2 3 equals to cot theta. Also gamma 3 1 3 equals to 1 by r, and gamma 4 1 4 equals to 1 by 2 mu dash. So, all the non-zero components of Christoffel symbol of second kind have been calculated, and the values are given here. So, we can also see that the Christoffel symbol of first kind for 2 2 comma 1 equals to r, 1 2 comma 2 equals to minus r, and 2 3 comma 3 equals to minus r square sin theta cos theta. Similarly, the Christoffel symbol of first kind for 4 4 comma 1 equals to minus 1 by 2 e to the power mu dash. Christoffel symbol of first kind for 3 3 comma 2 is equal to r square sin theta cos theta, and 1 4 comma 4 equals to 1 by 2 e to the power mu dash. Three 3 comma 1, the Christoffel symbol for first kind for 3 3 comma 1 is coming to r sin square theta, and for Christoffel symbol of first kind for 1 3 comma 3 is equal to minus r sin square theta. So, with the help of all these Christoffel symbols of first kind and second kind, we can calculate the components of Ricci tensor, which we know that it is the tensor of type 02, and it denoted by R I j, and the expression for R I j is equal to this one, del square log root over mod g del x I del x j minus del x alpha Christoffel symbol of second kind alpha I j plus gamma alpha beta j gamma beta alpha I minus gamma beta I j del log root over mod g by del x beta. So, this is the expression of R I j which we have obtained earlier in our earlier chapter. So, just putting the values of all these Christoffel symbols and the values of the g, we get the components in this way. That means R11 have this expression, that is del 2 log root mod g by del r square minus del x1 gamma 1 1 plus gamma 1 1 1 gamma 1 1 1 plus gamma 2 2 1 gamma 2 2 1 and so on. So, we can just put the values of I and j and we get the expression for R 1 1, and again if we put the values of Christoffel symbols and the value of g, we get, after a brief calculation, we have R 1 1 equals to 1 by 2 mu double dash, that means the second order derivative of mu with respect to r, plus 1 by 4 mu dash square minus lambda dash by r minus 1 by 4 lambda dash mu dash. Similarly, we can get R 22 and which is equal to the value of R 33 with multiply by cosec square theta. So, this is the relation between R 22 and R 33 and the expression is coming to this one. R 44 has this expression, that is equal to e to the power minus lambda plus mu and within the third bracket this expression, and other Rij's are 0 for I not equal to j. And with these components of Rij's, we have the curvature invariant, that is capital R equals to Gij Rij. That means, the scalar curvature of the space is coming to this expression, that is equal to 2 by r square plus e to the power minus lambda minus 2 by r square plus 2 by r lambda dash plus half lambda dash mu dash minus mu double dash minus half mu dash square minus 2 by r mu dash. And thus, the necessary and sufficient condition that a space with spherically symmetric metric be in Einstein space is that r equal to 0. Now, from r 1 1 equal to 0, we have this condition. The value of lambda dash by r is coming to this. And from r 4 4 equal to 0, we have this expression, e to the power minus lambda plus mu in the bracket, this one is equal to 0. Now, simplifying this value, we get this relation minus 1 by 4 mu dash lambda dash plus half mu double dash plus 1 by 4 mu dash square equal to minus 1 by r mu dash. So, using the above result, we get lambda dash by r equal to minus 1 by r mu dash. That means, if we integrate, we get lambda equals to minus mu plus constant. Now, from r 2 2 equals to 0, we have this expression e to the power minus lambda within the bracket 1 minus half r lambda dash plus half r mu dash equals to 1. Now, if we set e to the power mu equals to nu, then mu equals to log nu and mu dash equals to 1 by nu dash. Therefore, mu dash e to the power mu equals to nu dash, and the above equation reduces to nu plus r nu dash equals to 1. That means, nu dash by 1 minus nu equals to 1 by r. So, writing in this form, it is d nu by 1 minus nu equals to dr by r, and integrating we get nu equals to 1 minus k by r, where k being a constant. Again from G44 we have e to the power mu equals to nu, that is 1 minus k by r. We can say this one as k or kappa, whatever you like. So, thus the metric takes the form this one, ds square equal to minus 1 minus k by r to the power minus 1 dr square minus r square d theta square minus r square sin square theta d phi square plus c square 1 minus k by r dt square. So, this metric is known as Schwarzschild metric, which was given by Karl Schwarzschild in 1916, and the space time in general theory of relativity is called Schwarzschild space time. Now, a space time is called static if there exists a special coordinate system for which all the metric coefficients, that means the coefficients of x, y, z are time independent, and also the line element is invariant under the time reversal. That means, if we take instead of t as minus t, then the line element will remain same. Now, the Schwarzschild space time is a good example of a static space time. That means, it is invariant under time reversal. Thus, in module 5 of chapter 10, we have learned a special type of metric in general theory of relativity known as spherically symmetric metric, and we have deduced an expression for Schwarzschild metric, which is a special type of spherically symmetric metric, and it is a static metric. That means, it is invariant under the time reversal. All these things we have seen in this module. So, with these things we end this module.